Swayam Prabha. Digital India. Educated India.
Welcome back. So in last lecture we were talking about that how the folds are formed and how we see the interlinking of the fold, two folds to give rise to a larger anticlinal fold. And as I was talking about on that day that this was one of the best site which we identified for trenching to see the ancient signature of the ancient earthquakes. So this is a tip of a plunging anticline which is moving in this direction. So whenever there is a rupture or displacement on this particular fault, that is in southward fault, then what we envisage is that this will grow further towards the east. So we identified, as I told, that the best place was the this notch of the anticline or the nose of the anticline, which we said, and then we picked up that if there is a deformation in the quaternary deposits, a very young deposits, then that will be helpful for us in picking up the most recent earthquake which has occurred along the southward fault during historic past. So fortunately we found a very beautiful artificially cut fold or the ridge which was been dug for the irrigation purposes, and we found vertically stacked Mesozoics and tertiary rocks, and there is a contact between the tertiary and the quaternary. So we decided to trench in this area. So this was the panoramic view of the fault scarp, which runs in almost like east-west direction, and this fault scarp is facing towards south. So south facing fault scarp. So close up of that. So we identified, and this usually we do what we call to identify the ancient earthquake signatures preserved in the stratigraphy. So that is known as paleoseismology. So we opened up the trench. So this was the area which we marked and selected based on our experience, and we believe that the fault is running somewhere over here. So this was a small, not very small, but yes, of course, a pit was open using JCB backhole to look at the section, because this will give us the deformation pattern. If you study this section open here, we will be able to see. So for us, we were very confident that the fault is running somewhere over here, and this was the trench which we opened and stratigraphy which we studied. And after demarcating all units, what we see this the trench, and this the log of the trench, which shows the deformation or the folding of Mesozoic rocks from like unit A3, and then you are having the tertiary deposits or the tertiary succession which also got folded and displaced. So this is the faulting which we see in section. So the F unit was the youngest, belongs to the younger deposits F and G, and the fault which has displaced this over here, it dies out somewhere here. So what we say that the event, the most recent event, took place after the deposition of unit F and before the deposition of unit G. So after, we say after the deposition of unit F and before the deposition of unit G. Now why we say this? Because this was the surface at the time of the earthquake, and which got displaced. So if this was the surface before the earthquake, that means this existed before the event. So this already the deposition took place. So the event occurred after the deposition of unit F, and since it is capping this deformed unit F, the deposition of G came up later on. So we say the event took place before the deposition of G took place. So this gave us a bracket between the bracket of the event actually, that we were able to pick up. So this is extremely helpful, and this we suggested here that there will at least 2 events, and those 2 events, not 2 but at least 3, but 2 events were responsible for resulting into an great damage to Dholavira site, that is an Harappan site, which is not very far from this fault. So these are the interpretation which we made, and based on the paleoseismic studies. So I'll stop here, and we will continue in the next lecture. What we will talk in the next lecture, we'll immediately start that. We'll talk on the ground deformation, which is extremely important for understanding that what will be the site effect at the time of the earthquake, even if the fault is sitting away from the site. Then also we should not underestimate that in terms of the damage, that we will not be able to experience the damage if you are even sitting away from the fault. So that we will talk about, because the deformation is one part which will take place on the fault. For example, I'll just put the sketch here, like you are having a fault here and you are sitting somewhere, the town is somewhere here. Okay. So of course the maximum peak ground acceleration will be at this point, but if even you are sitting away, depending on what is the sediments one, okay, and depending on that what is the rock type you are having, the deformation or the site effect will be different. So that we will discuss in the next lecture, what we call the ground effects. Okay. So this we need to take into consideration. If you have whether your houses or the settlement is sitting on the soft sediment succession, or your houses or the buildings are sitting on the hard rock. So this is going to change the scenario or the pattern of damage over the time. Now, evaluation of the earthquake hazard is extremely important, because as I told in the previous lecture, that even if you are sitting away from the epicentral area, you are bound to get affected because of the seismic waves which are traveling from far distance. Okay. So depending on what are the type of material which is on which your site is located, that thing will bother us. Okay. So for seismic hazard evaluation, mainly what we look at is the seismicity and ground deformation of the area. So we try to see the historical seismicity and then ground condition. What is the type of material on which we are putting the foundation of our structure? That is extremely important. Effect of earthquake vibrations on sediment type, because different type of sediments, like if you are having sand, if you are having clay, the vibrations, the amplification will be different from place to place. Then we are having seismic investigations, then duration of the seismic event, how long was the event, and how long it is expected when there will be a next earthquake. Then magnitude of earthquake is also important, because depending on that, where your fault is and where the epicenter will be, how far you are sitting from the fault line, the magnitude will play an important role in terms of the ground shaking or the intensity of the ground shaking. And then we also try to look at that what are the precursory events which can help us in identifying or predicting the future earthquake. This is not very much like we did not get and what you say is that we have not achieved fully in terms of the precursory events, because it is a bit difficult to say or to tell or to pass on the warning that at what time and the earthquake will occur. But at least we are able to understand and know that, of course, this area is prone to earthquake, and what will be the expected magnitude for the next earthquake. That is a bit sure for that. Along with that, measurements of electric and magnetic field. People have been working on this, and of course, as we have discussed in one of the lectures where we were talking about that magnetic field of the earth and all that. So when there is a disturbance or the ground shaking or the sudden release of the stored energy, some changes will be observed in terms of the magnetic and electrical field. So people are doing research on this, and hope in future we will get success looking at such information. So geological and geomorphological records, this what we are doing, because as I told in the previous lecture and where we were talking about one of the case history from Gujarat, Kutch along South Wagad fault, all deformation which have occurred, if the rupture has reached right up to the surface, then they will get preserved in the geological records, and geological records we can say that they will be preserved in the sediment records. And geomorphology, and the different landforms will be found, which we say tectonically formed landforms. Plotting of seismicity data on geological map. This is a preliminary exercise. Usually we do try to understand that what is the pattern of this seismicity, whether it is aligned along one particular fault or it is diffused seismicity. If we see if it is getting aligned along one particular fault, then there are one can say that okay, fine, this earthquakes are triggered along this particular fault, and there is a likelihood of having a bigger earthquake in future. So, and study of accelerogram. So to evaluate the seismic hazard, seismologists or geophysicists, they try to look at the seismogram or the accelegrams of the previous earthquakes, which can help in terms of understanding that what was the peak ground acceleration at that particular point or the site of interest based on the previous events which have occurred in that particular area. So that can help us in understanding the site effects of the site of interest. So seismicity and ground conditions, if we take what we see is that if you are having in suppose an hard rock and a particular magnitude earthquake has been triggered, then in sedimentary rocks you will have different amplification, and this is based on the propagation of the surface wave. And in alluvium, which is a loose material, the amplification will be a bit higher as compared to the sedimentary rocks. But as soon as you get into the very fine deposits, silt and mud and all that, then you will have an amplification will be very, very high. So if you consider this as an Himalayas and this as an Indo-Gangetic plain, then one can understand easily or say that this area is going to be affected more, because the amplification will be much higher. So ground shaking will be much high as compared to what we will see in the hard rocks. Okay. Of course, the Himalaya is not purely consist of the hard rock; it also have fluvial and marine deposits. So we will face something like what we see in the sedimentary rocks. So amplitude of seismic waves and acceleration varies from place to place. It is much greater on deep, thick alluvial than in the rocky terrain. However, some well built rigid buildings suffer less damage on alluvium than on the rocky. So one has to be extremely careful that they use while doing the construction or coming up with the structural analysis. They should use the BIS code as a building codes which are assigned for that particular region, and that is one of the important part where the geophysicists and even the structural engineers, they study the accelegrams, because they want to understand that what was the peak ground acceleration by a particular earthquake which has occurred in the past or the recent past on particular fault. But poor construction will be more affected, and if you ask us, we would say that most of the construction done in the alluvium in the Indo-Gangetic plain is in most of the areas, villages and small towns, it is poor construction. So chances of having in greater damage we cannot rule out. So effect of vibration on grounds. So what basically happens is that stronger vibrations during earthquake can affect the portion of the upper crust comprising thin pile of loose unconsolidated sediments. Now this cohesiveless sediments, mainly sand and silt, undergo compaction. Because of the cyclic stress, they will go under compaction. Loosely packed water saturated sediments can lose all shear strength and behave like liquid. So as soon as they loses the shear strength, the structure which is sitting on the top of that surface will collapse. This phenomena is known as densification. This will result into increase in pore water pressure, which eventually result into the formation of sand boils. I will show some example of the sand boils from Great Run of Kutch, which we observed during 2001 Bhuj earthquake. And this phenomena is termed as liquefaction. So for liquefaction, what we see here is that we have an capping unit which is not water saturated, which is not porous, as compared to what we are having the porous deposits. Here we have a sand, and we are having a very typical bonding nature of the sand. There is an arrangement of the sand grains, and in between the available pores are filled up with water. So this remains under a typical condition where there is nothing is happening, no if whatever the overburden you have, but this will not collapse. But as soon as you shake this, okay, so these are the pore pressure and the pore water. So before earthquake, the grain remains packed due to friction between them, and the weight of the ground is supported by the sand grains. So this will be taken by the sand grains and all that because of their arrangement. But when there is a cyclic stress, because when the seismic wave passes through such units, okay, or the uppermost part of the earth crust, then it will disturb this arrangement, and that will result into the compaction. So during earthquake, shear wave results into increase in pore water pressure, causing formation of sand boils at the surface. So liquefaction is defined as a phenomena that causes transformation of water saturated sandy or silty, or you can say cohesionless sediments. It transforms the material into liquefied state due to increase in pore water pressure. And since the pressure is low towards the surface, the high pore water with higher pressure will break the surface and come out of the surface. So you will see, I'll show some examples that when there is a compaction here because of the cyclic stress, then this material has been, the top layer has been broken, and then material which is over here, because of the compaction and high pore water pressure, it will rise up, break the surface and come up and ejected to the surface. So this is one short movie which talks about that how will three buildings engineered equally on different bedrock react to an earthquake. So same building with same code but constructed in three different areas. So different bedrock, how they reacted. So building motion will be exaggerated to emphasize the wave. Here it is, they have emphasized here, and let's see what it shows. Okay.
The motion of similar buildings on different bedrock will be exaggerated to show the arrival of compressive P, shearing S, and rolling surface waves from a regional earthquake. 3 consecutive seismograms will show the changing frequency and amplitude resulting from the change in rock type. The initial P wave arrives with a compressive bump and rarely causes much damage. The slower shearing S wave introduces a side-to-side motion that can throw loose objects to the floor and may crack walls. The rolling surface waves are the most damaging in unconsolidated sediment. As surface waves enter the sedimentary layer, they slow down and increase in size, causing buildings to roll. If not engineered for the motion, they can crack and tumble. But even a well-engineered building can sink during the shaking and liquefaction of underlying wet sediment. The first seismogram from the pink building on solid ground shows low amplitude, high frequency waves. When the waves hit softer ground, they slow down and increase in amplitude. It's this higher slowing roll that is so destructive during an earthquake.
I'll stop here. I'll continue in the next lecture. Thank you so much.